이름이 어떻게 되죠? 업무. 네. So one thing is next Wednesday, I have a business trip, so we will provide a video lecture instead of the offline lecture. Okay. So I mean, there's no offline class next Wednesday. Okay. This is 20th of March. Okay. Video will be provided in the Blackboard. Okay. It would not be online class, but we will provide videos in the Blackboard. Okay. Okay. And previously, we learned how to use the Pytorch library. Okay. So the important thing is these two functions, the low start backward, and optimizer dot step. Okay. When we call this low start backward, we calculate DLD sector for all the variables connected to the loss function. Okay. And then if we call this optimizer dot step, we update these parameters once. Okay. So this is two important code in the Pytorch. And the thing when you properly write the code in Pytorch style, then the thing you have to change for new application might be this definition of the network and the definition of the optimizer and definition of the loss function. Okay, so it would be very simple to implement the deep learning architectures. Okay. And this is another way to implement the architecture, deep architectures in Python, Pytorch using the class, right? So you have to define both things. The first one is the network initialization part, and the other thing was the forward function. For backward and parameter update rules, you don't have to implement it by yourself, right? We can just inherit them because they are same functions for new architectures. Okay, we don't have to implement that. And now we will implement the training part of this CNN architecture for the image classification task. Okay, so you already know this image classification task. We already explained this. So in image classification task, images are composed of the images having just one main object. Okay. For example, this line is having airplane object as their main object. Okay. And this lines, the images are having the automobile as the main object. Okay. So the task is categorizing each image according to their main object. Okay. And in this data set, which is very famous, it has 10 digits inside the images, each image, right? And the digit it has becomes their own class, okay? So their class is 3, 4, 2, 1, and so on, right? So this is also doing the image classification task, okay? Also in Caltech 101, it's also the data set which is developed for the image classification task. So this is the largest scale, the most big, the biggest data set in the world for the image classification. Okay, it has 1,000 classes and have million scale images. Okay, Anyway, this is the data set in the image classification task. And I will start this discussion from the most simplest classification algorithm, which is called as logistic regression. Okay, even though its name is regression, and actually their name is similar to linear regression, right? But this is not same. Okay, this is the regression algorithm that involves the linear operation, right? This kind of operation is linear. So linear regression is the algorithm that have this kind of operation and does the regression task. But logistic regression, that actually performs the binary classification. So in that sense, they are not same, okay? But their operations are similar. So inside the logistic regression, we have the similar operation, but at the end, we have another layer called as sigmoid function. We already learned this sigmoid function, right? So this was the sigmoid function, which is used as the nonlinear function inside the CNN architecture. And from -infinity to infinity values, x values are spanning from -infinity to +infinity, but their y values are confined in 0 to 1 values. So that's the sigmoid function, okay? So this sigma, we normally write it as the sigma function, but their actual formula looks like this, okay? Sigma x is actually this one, right? And this is inputting this minus wx plus b inside this this location, right? So this is our logistic regression formula. So from the original input, we apply first the linear operation on that, and then input it to sigmoid function. So that's the logistic regression formula, right? So this is our output, but this output will be confined in this range, right? Because we input our output of this linear operation to the sigmoid function. So the final output will be bounded to 0 and 1, right? The thing we will do next is we will threshold these g values. So if g is larger than 0.5, our final output would be 1. And if g is less than 0.5, we will regard it as 0, okay? So, I mean, we will threshold this value with 0.5, okay? Actually, our final output in logistic regression is binary value, 0 or 1, right? And they indicate that the class category, okay? So this logistic regression can perform the binary classification, which is the task of classification, but having only 2 classes. The first class is 0, and the other class is 1, right? So, and this G value itself could be regarded as the probability, okay? Probability for having a class 1 or the other class, okay? So this is the very simple algorithm for classification, having just 2 classes, okay? And maybe for the regression task, linear regression task, we use just the mean square error loss, right? So for the linear regression, our network, their output looks like this, but we use somehow mean square error loss, MSE loss, which closes the final output to its ground truth value. We use this type of loss function, right? because it was the regression task, our output value is continuous value. Our ground truth value is also the continuous value. Our aim is to make them similar, right? That was the regression task. But in logistic regression task, our output is 0 or 1, right? And our ground truth is also 0 or 1. That's the classification task, right? Are you guys following this? Okay. So the loss function is becoming different from the regression task, okay? And actually, this is frequently used loss function for the classification task. And this is called as binary cross entropy loss, BCE loss. This is the binary cross entropy loss. And actually, these two formula is representing the same one, okay? You have to fill that first, okay? So this is denoting that when yn is equal to 1, the loss function would be this. And when yn is equal to 0, the loss function would be this, right? Yn is denoting the ground truth value. And Zn is n's samples output, right? And Yn is denoting n's samples ground truth, right? So when ground truth of some sample is 1, we will apply this loss function for that sample. And for when the ground truth value is 0, then we will apply this loss for that sample, right? We can represent that in this formula, right? When Yn is 1, this becomes 0, right? Because of this term, right? When Yn is 1, this becomes 0. So this is same as this, right? And when Yn is 0, this becomes 0 and this remains, right? So this representation and these two are same, right? In that sense. Okay, that's the first thing we have to understand. And the other thing is, when ground truth is 1 for n sample, we have to we normally minimize the loss function, right? So this is ln zn function, right? When x-axis denotes zn, this might be the graph for ln zn, right? Then this would be the graph for minus ln zn, right? And normally we will minimize this value, right? And the Zn will be bound to 0 and 1 range, right? Because we applied sigmoid function, Zn will be bounded to this range, right? Within this range, this value is 1 and this is 0, right? The Zn will lie on this range, right? For this range, which point are minimizing this graph? That is 1, right? Right? So by minimizing this loss, we can enforce Zn go to 1, right? When ground truth is 1, we can enforce Zn goes to 1 by minimizing this loss, okay? That's what we want, right? And when Yn is equal to 0, when ground truth is equal to 0, if we minimize this, then 1 minus g when n will go to 1, right? If you draw the same graph by interchanging this this into this, then you can conclude that when 1 minus Gn goes to 1, this value will be minimized. It means Gn should go 0, right? So when Yn is equal to 0, when ground truth value is 0, we have to enforce output Zn go to 0, right? So that's happening here, and when here, when Yn is equal to 1, we will enforce Gn to 1, right? That happens when we minimize this loss function, okay? So it makes sense, right? So this binary cross entropy loss is used for this logistic regression task instead of this MSE loss, okay? So that coincides our aim, right? This is the classification, binary classification task, and ground truth is 0. Then we have to enforce our output to go to 0. And when the category is 1, then we have to enforce our output to go to 1, right? So that can happen using this BCE loss, okay? So we use this BCE loss for achieving this logistic regression, okay? Then, I mean, if the sample's output, sample's ground truth is 1, then we can have the value close to 1, but not exactly 1. But if we threshold them using this 0.5, because there's output become close to 1, we can, by thresholding them using the 0.5, we can obtain this 1 value, right? And otherwise, we can obtain this 0, right? So that's the way we perform this binary classification, okay? And this is the code for implementing the logistic regression, okay? So this is the part for preparing for the data. So we will use the iris data. This X is the input image, not image, maybe. And Y is also the vector, not vector, some labels, the class information, and X is some vector, right? Anyways, we load them from the this iris dataset. So this code is already implemented in the Pytorch. So this package, so we can just call this function to load the data, okay? And we sample the first 100 data samples, okay? And we define these 3 things, and using the same code, same training code, we will train the logistic regressor that performs classification on this iris dataset, okay? And the thing you have to see is this loss function is different, become different from previous linear regression task. So now we are using BCE loss, right? Rather than the MSE loss, okay? So that's the difference. We only can change this simple loss for implementing logistic regression instead of the linear regression, right? Because logistic regression, it involves this linear operation inside, right? And we apply sigma, the sigmoid after that. So our net architectures are just the linear function, right? But after in the forward function, what we do is we input the input values here into the net, which is the linear layer. And this is H indicate the intermediate output. So this becomes H, right? And then we apply the sigmoid function after that, right? Then this becomes some continuous value in between 0 and 1, right? This is the logistic regression's output, right? And by applying BCE loss, we can train our output becomes close to 1 when the ground truth is 1, and becomes close to 0 when the ground truth is 0, right? So this is the part for training our network. And then in the inference time, when given the input to the network and applying the sigmoid, we can have the value between 0 and 1, and we can threshold them and can predict the final class, right? Okay. So this is the simple code that can achieve the logistic regression. Okay. Any questions here? No. Okay. And this is another code which is similar, but this part is slightly different. Okay, so this is quite detailed, but I included this. So if you use this BCE with logits, then this is already having a sigmoid inside the loss function. So this loss function will apply sigmoid first, and then apply BCE next. Okay. So in this part, previously we have the code for applying sigmoid by ourselves, but here we don't have the code for sigmoid, right? So this is different style implementation. So if you search for Pytorch, their library, their code command, then you have to manage this kind of details, right? So yeah, but their functions are almost same. So I want to visualize their values are same. Okay. And so far we learned how we can implement the binary classifier, right? But now we will extend our classifier into the multi-class classifier. Okay. So binary classifier that can have only 2 classes, 0 and 1. But in multi-class classification algorithm, we can have multiple classes. Okay. We can categorize input into multiple classes. Okay. That's the multi-class classification. And for implementing that, we have some special layers, okay, similar to sigmoid maybe. And also we need to extend our BCE loss, okay. And this is the layer for the softmax, okay. And what happened here is we have in the final layer of the CNN, we may have 1 by 1 and number of class dimensional vector. And this, we wish this vector is representing some probability for each class, okay? But in reality, we need further processing because each entry of this vector is having very large scale values, right? So when learning the CNN network, intermediate responses are not bounded. So their values are quite big, okay? But the probability have to have this kind of characteristics. So let's say each entry as n, then let's say this is n-dimensional vector, maybe c-dimensional vector. Then anyways, this entries sum have to be 1 to make this each entry have the meaning of probability. Then their sum have to be 1. And at the same time, each en should be larger than 0, right? There's no probability having less than 0, right? So each entry had to have positive value, and at the same time, their sum have to be 1, okay? So for this, we apply this softmax layer, okay? Softmax layer, it has the formula like this, and of course they are differentiable, right? And we apply exponential function for each entry first, and then we normalize them by their sum, okay? So by applying exponential, we can meet this condition, okay? The exponential graph looks like this. For the input values from -infinity to +infinity, we can guarantee their output is positive, right? By applying exponential function. This is exponential function, right? And by normalizing them by their sum, we can ensure each entry's sum is equal to 1, okay? So that's why we involve the softmax layer to transform these unbounded responses to the probability, okay? Okay. Any questions here? Not, this is easy, right? Okay. So now it can have some conditions to be the probability, okay? And then we will apply the cross entropy laws, which is the extension of the binary cross entropy laws towards the multi-class classification, okay? So it has the similar form as the this binary cross entropy laws, okay? So minus ln class, okay? And you can think this as the the cross entropy is the extension of this towards the multi-classes. So we first multiply the class itself with the ln output, okay? So this is the same formula for that. So this is the ground truth, and this is the output, okay? And we apply log for our output, okay? So this P is the one hot encoded vector having just one for ground truth index, okay? And Q of X is the prediction, our prediction having multi-dimensional probability, okay? So this is the cross entropy loss. But we can extend this to these two terms, right? And P of X is the ground truth, which is not variable, right? So this is constant, and this is actually the thing we will minimize, okay? The Q is variable, so we will actually minimize this term. And this is actually same as the KL divergence, which is the formula that calculate the distance between these two distributions. Okay, so this is minimized when these two are same. When P and Q is same, this loss function have the minimum value. Okay. So actually, by minimizing this cross entropy loss, we can enforce our ground truth, same as our final prediction Q. Okay. So yeah, actually, this is same as the KL divergence between P and Q. So this becomes minimized when P is same as Q. Okay, so by minimizing the loss function, we can achieve this. Okay, and this is code for implementing the cross entropy laws. Okay, so in the Pytorch, you have this nn dot cross entropy laws function. Okay, but important thing is when you define these laws, and when you use these laws, input and target. Target is the ground truth. This location, your output should be here, right? Your output is some multi-dimensional vector, right? But when indicating ground truth, instead of applying it using the one-hot encoding, in Pytorch, you have to input their integer value. So target should be some one-dimensional vector having ground truth class index, right? And input, this part have to have some, how to say, some d-dimensional output. So this is 3 by d-dimensional output, and this is 3 by 1-dimensional vector. Okay. So, I mean, sometimes we confuse. We can get some error on this by making this as the one-hot encoding, and why, I mean, confused why this is not working. But anyways, you have to be careful about this. Okay. So are you understanding this? So now we will implement the LUNET architecture, which is the first CNN architecture proposed by Jan Li-kun in 1998. This was used for some digit classification, and it works fine for that application, but it was not generalizable to more large-scale applications. So after that, we used the shallow learning algorithm, but in year of 2000, we come back to this CNN architecture, right? Whose name is Alex. But anyway, this is the old architecture, but having the similar characteristics, so we will implement this, okay? So this is indicating the convolutional layers, and the later part, they are indicating the fully connected layers, okay? So this is some parameter initialization. So this is the learning rate and batch size, epochs, the iteration, and image size and classes. So we will, our input would be some images having digits inside. So our aim is to classify images according to their digit class. So there are 10 classes, okay? And this batch size is indicating how many images are processed parallel way, okay? So we will simultaneously process 32 images at once, okay? So it depends on the memory, right? And sometimes it affects differently to the final scores, okay? In theory, it shouldn't, but sometimes it can affect, okay? Anyways, this is hyperparameters, right? And this is the definition of the LUNET architecture. And we have two functions, samely as before, right? So in the init function, we will normally define our network architecture, right? So first part, we have the convolutional operation, right? And the later part, we have the linear operation that processes the 1D signal, right? And previously, the tangent hyperbolic operation was used, but later this was transformed to ReLU layers, right? Because ReLU have the better characteristics, okay? So anyways, that's the definition used in LUNET architecture. And we have to define our forward function. So we first apply the first convolutional layers and then flatten it and apply the classifier, the fully connected layer later, okay? This is the definition of the LUNET architecture, okay? And then the thing we have to explain is this. So in previously, when implementing the regression and multi MLP, what we have done was we iterate through we actually sometimes omit the data load part when doing this, but and maybe this time the data was very small in scale, so we apply this data at once and we iterate it multiple times. But in CNN, when implementing the CNN, the scales are gradually become larger, and we cannot do this. We cannot say all the image data inside just one variable, okay? So now we have to require some special module that load data, okay? But this is not mandatory, but I highly recommend to use this data loader, okay? Because it provides you the convenient way to load the data, especially the data loading itself takes some time, right? During the training itself takes a lot of time, like a week, few days to few weeks it can take. But loading data, that can also slow the training time. I mean, so data loader provided by the Pytorch, it can help you to accelerate the data loading part, okay? For example, not here, maybe. I'm not sure, but in data loader, maybe not in this code, but in data loader, you can specify how many, you can specify you will use the threading, which is the parallel processing technique, right? You can just specify to use it or not in one of argument in the data loader, okay? So anyways, it provides easy interface for loading the data. So in that sense, I highly recommend you to understand and use this data loader, okay? But it is, of course, mandatory. If you don't understand this part, you can still load the data by yourself and can supply the data to the training code we already learned, right? But this data loader is another part which is important, okay? So in Pytorch, it provides the class whose name is data loader, and also it also provides the dataset class and data loader class. These two are core part for helping you for the loading the data in Pytorch, okay? So for the dataset class, you have to define how your XY pairs are defined, okay? And also in Pytorch, you can easily load the famous datasets, just calling these things. So MNIST dataset, this is the famous dataset, which is frequently used. So the Pytorch already gives you the interface for loading the MNIST, okay? And you can also specify some of the arguments. So if you do not have data set before executing this command, okay? And also the transformation, we need to resize the image itself, right? Before applying the CNN architecture, So this kind of operation is could be implemented easily, right? You have to define trans variable, which defines the transformation for resizing here, okay? And then you can specify it here, right? So by doing this, you can apply the same transformation for all the input, okay? Without implementing the code for applying resizing part by yourself, okay? So this is the merit for using the data loader. Anyways, the dataset class, you have to define how your XY pairs are defined, okay? And for the training and testing dataset, how your input X and output Y are defined have to be specified in datasets. And in data loader, using this dataset, specifying how your X and Y are defined, you will make the data loader. So here, this kind of defined batch size, how many images are processed at once are defined, and which data set you will use are defined. And shuffling means the index of the samples are shuffled or not, right? Is defined. So if you just make this flag as true, the sample order is randomly shuffled. This is critical for training part, right? So if we supply training data in random order, it can prevent the overfitting phenomenon, right? So for the training data, we can shuffle it, but for the testing, we don't have to do that. I mean, the accuracy of the testing data will not be changed depending on the order of the samples we supply. So normally for the testing data, we will not provide, we will not shuffle the data, but for the training, for preventing the overfitting, we apply shuffling, right? So anyways, the data loader, this is defining how to load data based on the definition of the data set, okay? So these two are important part when loading the data, okay? So if you go to this link, you can search for other frequently used data set defined in the Pytorch, okay? MNIST is one such example, but you can find another examples, okay? And also, you can even define your own data set for data loader. This page is showing that. So for using that, you have to define your own X and Y pairs, okay? You have to define your own dataset class, defining the input X and output Y, okay? And it have to have these three methods. Init function have to will be executed once when the class is defined, class is made, instance is made. So this part have to have data itself or have to have some path for the data, right? So if the data scale is small, you can specify all the data itself in this init method. But if the data becomes bigger, you have to specify their maybe location in the hard drive, right? And this len method, it specify how many data are there, okay? And get item, this defines how your data are loaded, right? How your X and Y pairs are loaded, okay? So this time we just define this data X and Y directly in initialization part and just return it. But if the data becomes bigger, you have to specify some data locations in the hard drive in initialization part, and you have to load it using OpenCV library and return it, right? Anyways, in such things have to be defined in the dataset class, and using that definition, you can also define this data loader, okay? anyways, I recommend you to use data loader, right? And another thing we have to learn is stochastic gradient descent algorithm. So do you know what is the difference between gradient descent and stochastic gradient descent? Is there anyone who already know? Maybe most of you know. I don't know. 아는 사람 있어요? SGD랑 GD 다른 점 아는 사람 있나요? 다 알지 않나요? 아닌가? 대부분 어렴풋이는 다 알지 않나요? So, I mean, gradient descent, stochastic gradient descent, they are sharing the same formula, right? But gradient descent, when to update is different between these two. So gradient descent, it see all the data at once and then update this for all data once. That's the gradient descent. But stochastic gradient descent, it sees only the partial data. It does not see all the data, but see only partial data and then update this multiple times. Okay, so we can represent it in this way. So gradient descent, we have to see all the training data and update once. Okay, but stochastic gradient descent, we see partial data and update multiple times. Okay, but fortunately, this performs better because the training data and testing data are different. Okay. Training data is not equal to testing data. So we have to update our parameters for gradient descent using only training data, right? When using the gradient descent algorithm, our model will overly fit it to the training data because when seeing all the training data and update one step, this is optimal for that data, the training data, right? So when the model is obtained via these things, it has the possibility that the model cannot be good for the testing data, the new data, right? But this stochastic gradient descent, in theory, this is not optimal compared to the gradient descent. But we will test our model on the new unseen data, right? For that sense, this could not be optimal for the training data, but this could be better for testing data, right? So because of that, so if we denote this in the parameter space, this black line is representing the gradient descent steps. So it is optimal for the training data, right? We can find the optimal minimum, but this red indicates the SGD, right? The individual steps could have noise because it sees the partial data, right? But this noise could help to be generalized to the testing data, which is unseen during the training, okay? So we use this stochastic gradient descent. And also in other aspect, if the data, training data is large, we cannot easily perform this gradient descent. If there are million training data, we cannot wait for model during the training to see all the data because it may take few days and few weeks, okay? I mean, when using the gradient descent, when seeing all the data after maybe 1 or 2 days, our model will update just once, right? The training will be very slow, maybe, right? But in reality, we use the stochastic gradient descent, so we update our model multiple times during that 1 or 2 days, right? And actually, it performs better than the previous one, right? Okay. So actually, this SGD is also a good way of training using the large-scale data set, right? Kind of practical way to train the model, right? So we will use this SGD and also the data loader when implementing the LUNET architecture, okay? But the core part is not different from previous one. We will initialize our gradient to 0, and we will apply the forward rule, and then we will apply the backward and gradient descent update. This is for visualization purpose, okay? These lines are not changed much, right? But different thing is, from the training loader, which is defined by the data loader, we will load only the partial data, right? Differently to previous one, we will have batch number of X and Y, right? Like now, okay? And we will update our model for that batch size, okay? This is actually seeing the partial data, right? And this is actually the implementation of the SGD, right? But when you see the code implemented for the MLP or linear regression, because the data itself was small in scale, so we save all the data in the same variable and apply these things at once. That's the GD, right? But now we load only the partial data because the data is big, right? And anyways, we do that, right? Are you guys understanding this? Okay. So this is the core method for training for each batch, okay? And this is the batch testing code. The difference is we don't have this backward part. Besides that, everything is same, okay? So we only do the forward pass, and that is testing, right? And also important difference is this flag. Model have to be in training mode when applying the gradient descent, and model have to be in evaluation mode when applying the testing, right? Okay, you don't have to forget this, okay? And also there's no backward part in the testing code. And this is the loop for, the training code for multiple batches. So this is the epoch, which means seeing, one epoch is, one epoch corresponds to seeing one whole data. So if our epoch is 100, then it means we will see all the data 100 times, okay? And here we use the training method we defined previously. This is the training method. And we will apply the same method, okay? And, sorry. No. So this method is not merely seeing only one batch, but anyway, this for loop terminates when seeing all the data once. But each X and Y are indicating, each X and Y here is indicating batch-wise. The batch size was set as 32 before, so this X and Y, they are 32 samples, right? For each this for loop instance, we are processing 32 samples at once, but this for loop continues until we see all the batches, all the data, right? So this train method is actually the code for iterate through the whole data once, okay? And this is the code for visualization, okay? And also, this is the code for initializing the networks and optimizer and the loss function. Here we are using the cross-entropy loss we learned, okay? So this is the code for implementing the CNN and their training, okay? This is the testing part. This is the testing for entire testing data. So for epochs, we learn our model for one iteration of the whole data, and also we test our model for one iteration of the testing data and visualize it, and we loop through it, okay? Then you can see kind of result, right? From this log, you can see this kind of log, right? And it indicates the training loss, testing loss, and accuracy, okay? So you can see as epochs goes, the loss becomes smaller and the accuracy becomes larger, okay? But the previous code is using the CPU, okay? So you have to extend this towards the GPU, right? And in Colab, it also provides you the GPU. And if you set your own machine, then also maybe you have, if you properly set your GPUs in your machine, then you can also use the GPUs, okay? So if you add torch, and if you print out this value, it indicates whether your machines are having the available GPUs or not, okay? In the Colab, if your flag is false, then the thing you have to do is in the menu, you can select this and you can select GPUs, okay? After that, you can see your GPUs are allocated, okay? And also in your local machine, you have to check this is true, okay, to use the GPU, okay? And when using the GPU, you have to copy your data and also your model to the GPU, okay? And the command to do that is this. You can just use this .2, or nowadays the newer versions of Pytorch have some new command for this. But anyway, please follow that. And anyway, the thing you have to do is copying the variables into device, GPU device. And device is defined in the root function. And also for the testing code, you have to copy your variables into the GPU. Okay, and also you have to add this argument. And your device is defined like CUDA or CPU. Okay, so if this is false, then your device need to be assigned with CPU. But if this is true, then you will apply this with CUDA. Okay. So after that, and also your model should be copied to GPU. So your model and data need to be copied to device, okay? This is also the command for copying your model to GPUs, okay? Using these simple things, now it takes a few minutes, okay, when training the same code. The results are same, but it becomes much faster, okay? So this is simple extension of the code to use the training in the GPU. Okay. And for later things, I think we can continue next time. Okay. So thank you. See you next Monday. Okay.